Welcome to this Alan Talks Tech video. If you'd like additional information on my technology videos, please visit my wiki at alantestwiki.pbworks.com. So exactly what is beamforming, also known as phase and gain? Well, if we look down on an access point and imagine it's in the center of a pond which it's just been dropped into, the RF energy will be radiating out just as waves ripple out from a stone when dropped into the pond. This will be known as an omnidirectional system, as only one transmitter is transmitting from the access. However, it's possible to steer the RF energy towards specific devices within the network using beamforming. On a diagram, we often show this as lobes. So, for example, with an access point capable of generating lobes of RF energy directed to specific points within the network, we can create either a constructive combination of energy or a destructive combination. Both, surprisingly, can be useful. The constructive combination is obvious, but the destructive combination can also be used when we're using multi-user MIMO in conjunction with beamforming to help separate the different clients. But how does this all work? Well, let's take a look at how constructive beamforming works. First of all, when we transmit from the access point, we transmit some RF energy in the form of a wave. It's possible to enhance a transmission by having two transmitters and transmitting two waves of energy. And obviously, if you put these together, this can create a constructive wave which increases the amplitude and the signal strength at the receiving site. But the problem arises due to the signal path. The two beams of radiated energy may take slightly different paths and arrive slightly out of phase. If the two signals arrive out of phase, we then get a destructive combination. For example, in the worst case, where we get a trough and a peak coinciding. These can cancel out, effectively creating a null field. So, how do we adjust the beam so that we can get the optimal amount of RF energy at the desired point within the network? Well, there are two methods. We could use the implicit method. The implicit method is allowed in 802.11 and it assumes that the transmit power and the receive power are the same. The adjustment to phase and gain is based on the assumption that the signal received by the access point has the same characteristics as the signal received by the client. There is really no intelligent feedback, and in practice this may not work very well because it's, to be honest, the wrong assumption. You can't assume that the transmit path is going to be symmetrical. It doesn't always work like this in RF. So let's take a look at the second method. The second method is the explicit method. 802.11 allows for the explicit method where we get feedback from the client on how the signal is received. The adjustment to phase and gain is based on what the client feeds back to the access point. The relative amplitude and phase on each of the receive antennas of the client is sent back in the form of a V table or vector table. This will provide the information for each subcarrier. These tables can be very complex. As many of you may realize, orthogonal frequency division multiplexing is used, and there are a number of different subcarriers. Each subcarrier can have its own attenuation and own variation due to the signal paths involved. This system, though, can provide an improvement of approximately between 2 to 3 dBs in signal strength. This may not seem very much, but it makes all the difference at the midway point to the outer edge of the typical range of the access point, enabling you to maintain a better quality of service. For example, for those of you familiar with QAM, instead of falling back to perhaps 64 QAM, you'll be able to maintain a 256 QAM signal, maintaining much higher throughputs. So how does this work? Well, on the left, we've got the transmitter or the access point transmitting the three radiated beams of RF energy, all of them hopefully slightly out of phase, creating the correct characteristics on the receive point for the optimal signal strength. But if the system is moving at all, if it's a mobile device, the matrix is going to have to be continually updated. So as the signal is received on each one of the antennas within the mobile device, or on even a single antenna, All this information is fed into a three-dimensional matrix. Depending on the number of antennas used and whether it's single-user MIMO or multi-user MIMO, the matrix table can become very large. And if it's moving, it may have to be updated approximately once every 10 milliseconds, even if you're just at a walking pace. So how does this system work? Well, the beamformer, or the access point, will send out an NDP announcement. This is a null data packet announcement to gain control of the channel. After a short interframe space, a training field is sent out, an OFDM training field, to calculate the steering matrix. This information, or this RF energy, is received by the client, it's analyzed, and its V matrix or V matrix is calculated and compressed, and this is sent back to the beamformer. The client in this case is known as the beamformee, and the frame which is sent out, the training frame, is often referred to as a sounding frame. So let's take a look at exactly what happens. If we take this access point, which is capable of a 4x4 system, if we switch on one antenna, again as before, we can see a simple radiated pattern going out from the access point to the client. If we switch on a second transmitter, a more complex pattern is generated. Now remember, with Wave 2 802.11ac, it's going to be possible to have up to 4 of the transmitters enabled simultaneously. This would create a much more complex pattern. But to keep things simple, and just to give you the general idea, we're going to stick with 2 transmitters. If we look at where the client is situated, it's situated in a normal signal path. At this point, there is really no benefit to having the 2 transmitters. The client is still receiving relatively the same signal strength. But at certain points, the signal strength has been enhanced due to the fact that there are 2 transmitters and the wavefronts are overlapping. So where we see an alignment in phase, the amplitude can be doubled to give us 3 dBs of signal strength, additional signal strength. But that's not doing us a lot of good, as the client currently isn't sitting in any one of these points. But if we move the signal on one of the transmitters slightly out of phase, say 10% out of phase, we can steer the beam. So by adjusting the phase, we can steer the beam, and we can in effect create an increased amplitude at the location of the client, possibly of 3 dBs. This will enable us to maintain a much better modulation scheme and therefore a higher throughput. Now, most people associate MIMO with spatial multiplexing today, and remember, spatial multiplexing is basically 2 different signals. Same frequency, 2 different signals. Transmit beamforming, though, is 2 times the data on the same signal. So we have one frequency with the data being transmitted twice. So with anything less than 4 antennas, it's really not possible to have spatial multiplexing and beamforming running concurrently. So to get the full benefit, we really do need 802.11ac. Now, if we compare where we were with 802.11n, 802.11n was really acting more in the form of a hub. 802.11n could provide spatial multiplexing, typically with 3 spatial streams, and support sequentially user number 1, user number 2, and user number 3. Now I'm showing on this diagram that we're actually using beamforming as well, but in reality very little beamforming was used with 802.11n, as the beamforming technology was typically proprietary. So the system is really running as a hub. You can only service 1 user at a time. With 802.11ac, if we have an 8x8 system, we can support up to 4 users simultaneously with beamforming. So this means that we can actually transmit to the users simultaneously. 4 users can receive data simultaneously. This is much more similar or more analogous to a switch architecture. And this is where one of the big benefits of 802.11ac is going to arise. Not so much in the throughput for each individual user, but its ability to support multiple users in parallel. So for densely populated halls, conventions, etc., users will be able to get much better performance, much better throughput. Thank you for watching this Alan Talks Tech video. I hope you enjoyed it. If you'd like to get more information on my technology videos with additional material, you can visit my wiki at alantestwiki.pbworks.com. Once again, thanks for viewing.